Okay, so it provides me a distinct pleasure here to give a tutorial about Soliton Microcombs. And I would like to, first of all, outline that a lot of the work I'll be presenting is the work particularly from current and past collaborators and also from former members of the group. And so I'd like to actually acknowledge up front here a few of them, in particular my collaborators Michael Gordetsky, Camille Brest, Tobias Herr, Christian Koo, Scott Papp, John Bowers, and Sunil Bava. And also former co-workers and current PhD students. Now, before starting, let me make just a couple of comments. So there's been a lot of progress in the field of Soliton Microcombs. And I'm only showing kind of a cross-section of work. And so for those in the audience, that if I may skip some certain topics that some of you may deem important, I already apologize in advance. In addition, I should also disclose that I'm co-founder of a spin-off that's called LigentTech that actually provides Silicon Nitride foundry service, so I'd like to mention that up front. Now, before starting this tutorial, I would like to actually take one moment to convey actually a rather sad message, and I wish I had more a pleasant first slide to start with. My longtime collaborator, Michael Gordetsky, with whom I collaborate for the last 10 years and who has been a real pioneer in the field of ultra-high Q microresonators, passed away this January due to disease. And it's with great sadness that he's not here today. And he made many contributions to the field. The most notable important contribution is that he was perhaps one of the persons that really started the field of high Q microresonators with his observation of ultra-high Q resonances in silica microspheres, which he made with Vladimir Braginsky already back in the 90s. These microresonators can be used to generate optical frequency combs, and optical combs have been featured here at CLEO for almost 2 decades, and they really go back to early ideas that Ted Henge and John Hall in particular developed on how to generate an equidistant spectrum by a method they called self-referencing. So self-referencing is a method by which you take an optical comb or a pulse laser source, and one of the key ingredients to generate optical frequency combs is the ability to measure the so-called carrier envelope frequency. And that implies that you need a spectrum that is 1 octave in bandwidth. And these octave spanning spectra can be generated by supercontinuum generation in photonic crystal fiber. And so that has been actually one of the key kind of principles of optical frequency metrology. Now, optical combs can be thought of, again, as equidistant markers in frequency space. So you have the carrier envelope frequency, which is kind of the offset of your first comb teeth. There's a repetition rate. And on a physical basis, the FCO comes about because the group velocity and phase velocity of light in pulses in a mode-locked laser need not to be the same. And for that reason, not every pulse is the same. So if every 10th pulse has the same envelope compared to the carrier, your FCO would be F-rep over 10. Now, these optical combs can be operate in 2 kind of ways. The first is called frequency synthesis. So imagine you measure using self-referencing the carrier envelope frequency, and you also stabilize the repetition rate and FCO to a quartz crystal, so quartz crystal oscillator. What you would be able to do is synthesize an optical frequency that inherits kind of the phase stability from the original kind of RF signals. And that's called frequency synthesis. So you synthesize an optical frequencies, and the precision of that frequency is limited by the RF clocks that you use. Now, in contrast, you can also run the comb as a clockwork in the reverse direction, so not from RF to the optical, but from optical to RF. In that case, what you would do is you would take, for instance, a stable optical reference, for instance, in a 1 Hertz laser cavity, stable that to one of the comb teeth, and thereby, by dividing by this large integer n, you'd obtain a repetition rate, now in the gigahertz domain, that is phase coherent with the optical carrier. And this allows you to generate exceptionally low noise microwaves, because you inherit in the microwave domain here the properties of your optical transition. This principle of optical frequency synthesis, or the division, is also the principle of an optical atomic clock. So you replace the new n here by an atomic transition, say in strontium, and can make very precise clocks, as we heard this morning. Now, optical combs are a commercial technology already since almost 2 decades, and they've been commercialized by MPQ, the group of Ted Henge, by Mendel Systems, and this is an early incarnation using a mode-locked femtosecond laser system operating here with TISAF. The more recent devices are really all built on erbium, and they're now kind of shoe-size kind of package, and are used for many applications in frequency metrology. Now, what are the applications of combs? So maybe one of the surprising aspects of combs has been in the last 2 decades that combs have seen a progressive number of applications that go far beyond just frequency metrology. And shortly after development of optical combs, self-referencing led to the first demonstration of an optical atomic clock. But combs today are used in many more applications, and this includes time transfer, so low noise microwave generation. You can use them to calibrate astrophysical spectrometers for exoplanet searches. They're used in molecular spectroscopy. They have been extended to the mid-IR. They have been extended to deep ultraviolet. They can be used for ranging, LiDAR, and also waveform generation. So in many applications, the ability to have a phase coherent spectrum of equidistant markers allows to different type of functionalities. Now, what's interesting to note, though, is that although combs are an extremely useful technology, they're not that widely spread. So in about 20 years, to give, for instance, one number, Mendel system has sold about 250 units. And so it's still, our ability to measure frequency in the laboratory is still mostly characterized by spectrum analyzers, optical OSAs, but we don't actually use the optical comb to measure unknown frequencies. So that's kind of a privilege that those labs that have optical frequency combs kind of have, and it's mostly compounded by also cost of the actual devices. Now, what happened over the last decade or so is that a new kind of technology has emerged, and there's a growing kind of field that is concerned with the idea of taking kind of optical combs and moving them into the chip scale. And the chart I've shown here is actually an image that I took from a DARPA program. So especially here in the US, it has been over the last 8 years a significant amount of funding flowing into microcombs. And the vision that DARPA formulated was to take an optical frequency synthesizer that is basically a mode-locked lasers and try to make a device that's truly chip scale. And the techniques that go into making kind of this vision happen are multifold, and we'll see that it's a combination of exploiting kind of techniques such as mode locking, solid transformation, but in particular leveraging then advances made in integrated photonics, that have in the last 20 years really excelled. And what I'd like to do in this tutorial today is tell you how close we are to this vision. And you will see actually that this vision is not completely unrealistic. You have devices that are not self-referenced, but actually take this type of form factor. And I'd like to in particular highlight and focus on some of the underlying physics that makes this process working. Okay, so how can you generate optical combs? And as described, one way to do this is to take a mode-locked laser and exploit the fact that a pulsed laser source gives rise in frequency domain to an optical comb. And the different technique was demonstrated already more than 10 years ago. And that is you can take a microresonator, so a device that can find light for long amounts of time in small volumes, that's dielectric in nature and has a third order nonlinearity, and you can pump that with a continuous wave laser. And if you do that, and granted you pump strong enough, and I'll explain what strong enough means, you can convert that single CW laser into an optical comb. So you use that, the process you're using here is parametric frequency conversion. And so this provides a distinct mechanism. There's no gain medium involved, so you just use here the passive third order nonlinearity of the material. And as we'll see, is the bandwidth of these combs is just determined by the material kind of transparency window, dispersion window, and finally also by the pump power that you have available. So how does this process work? So the process is that of four-wave mixing. So four-wave mixing is a 4-photon process by which you annihilate two pump photons in a generate version and generate a signaled idler photon. And due to energy conservation, the sum of signal and idler frequencies need to be exactly equal to twice the pump frequency. So inherently, this process generates equidistant sidebands. So if you have an optical cavity, and this cavity is characterized by a free spectral range, and in the talk today, I'll call the free spectral range D1. That's the FSR of the cavity. Now, an ideal optical microresonator, for various reasons, in particular material dispersion, and as we'll see, we'll actually engineer purposefully for that purpose, will also have a quadratic dispersion, and this is the GVD coefficient. And so the GVD coefficient implies that if you have anomalous GVD, that the free speckle range increases with frequency. Okay, that means that higher frequencies will travel faster, thereby leading to a larger free speckle range. So if you pump one of the microresonator modes, what will happen is that you have parametric fluorescence. So you have photons scattering to signal idler sidebands. And once that parametric fluorescence exceeds the cavity decay rate, you have parametric oscillations. Okay, and these sidebands then spontaneously emerge from the vacuum and give rise to two coherent sidebands whose amplitude grows with the pump power. Now, in contrast to conventional laser, that process, so the parametric oscillation, has one distinct feature. It scales with inverse Q squared, and that's because the parametric gain itself is also intensity dependent. Okay, and therefore it's not just gain equal to loss, but the fact is that the gain itself is also loss dependent. Okay, and that gives you an additional benefit here if you have a high Q resonator. Now, typically these processes are quite faint, but if you have a high Q device with small mode volume, this threshold can be extremely small, and we'll see devices today that have turn-on voltages or powers of milliwatt range or sub-milliwatt for parametric oscillations. Now, another way to understand kind of the threshold of this process, or what I want to mention is one more little ingredient, just for clarity, is to get this parametric oscillation to work, you need to have anomalous group velocity dispersion. So a perfect cavity with a perfectly equidistant grid would never show actually parametric oscillation. And the reason is that cross and self-phase modulation differ by a factor of 2. So cross-phase modulation, okay, is twice as strong as self-phase modulation, and therefore a strong pump will actually shift the eigenmodes of the cavity. And to compensate for that shift, you actually need a D2 that's positive. So all the cavities that exhibit parametric oscillations need to have anomalous group velocity dispersion. So it's an important kind of design parameter. Now, granted you have that, you can ask what is the threshold for parametric oscillation? And another way to kind of understand the threshold is to note that the threshold of parametric oscillations, okay, if you want to do a back of the envelope calculation, that corresponds to the power required to shift, okay, the cavity resonance, okay, due to the Kerr shift by half a line width. And this is also related to what's called bistability. Okay, so in fact, the parametric oscillation threshold, okay, coincides, okay, with the point where the cavity itself, due to the Kerr tilt, becomes bistable. So a cavity that will be weakly driven will have a Lorentzian line shape. If now you have a Kerr nonlinearity, what happens is as you increase the power coupled into the cavity, you get a Kerr frequency shift that tilts the cavity due to the redshift as a function of intensity, and thereby leads kind of to a region where the intercavity field is bistable. And we'll see in this talks that the region actually where there's a multi-valued solution of the intercavity field, that is actually related to Soliton formation. And the point where the cavity is shifted, okay, by about approximately half a cavity line width, that's the point when parametric oscillations start. And for those that are a little bit familiar with the microwave domain, actually in the microwave domain a similar process exists, and it's used for so-called bifurcation amplifiers. And it's the bifurcation here of the cavity that actually gives you gain. Yeah? So there's another equivalent way of understanding these parametric oscillations. Now, once you have signal idler sideband, the parametric oscillations become quickly more complex, and the key process to exploit for comb generation is not degenerate Fourier mixing, but non-degenerate Fourier mixing. So once you have generated a signal idler sideband, those sidebands in themselves can undergo a non-degenerate Fourier mixing process and transfer the initial pair of sideband spacing to higher orders. And that gives you then a completely self-consistent kind of optical comb. Now, one comment is in place. So what you generate here are equidistant sidebands, but note that the sideband themselves, of course, can still fluctuate. But the key is that the fluctuations in all the sideband spacings is correlated. And that is a defining feature of the optical frequency comb. So, so this process proceeds also in nature this way. And so this is an example of a microresonator where this process was studied. This is a microresonator with an exceptionally high Q, 100 million, and very high free spectral range. So the pulse or the spacing of the modes here is a terahertz, nothing that you can measure directly with a conventional beat node detector, but something you can measure with an optical comb. And so to measure and determine if this truly is an optical comb, what was done in the experiment is to measure the spacing of these terahertz comb teeth and measure that, okay, with an optical conventional fiber laser frequency comb. So if you use a fiber laser frequency comb as a reference, you can bridge those gaps of a terahertz, and you can subtract two adjacent free spectral ranges. And if you have a comb, what you expect is that that difference, okay, goes to 0. And this is what you see in this counting measurements. So here the deviation from the mean is 5 millihertz, just limited by statistical uncertainties due to finite kind of measurement time. And this proves that the spectrum here actually is an optical comb. Now, the comb that's generated here uses purely, as I said, the Kerr nonlinearity. But I want to make one comment that the Kerr nonlinearity, of course, is ubiquitous. And it also exists in many different kind of materials and systems. And there's a talk given by Jerome Feiss how to use that 4-wave mixing process not in a Kerr-driven cavity, but rather in a quantum cascade laser to promote the formation of laser frequency combs in the context of QCLs. And there's a tutorial here later this week. So over the last years, and really decade, I should say, there's been a large proliferation of platforms in which this Kerr frequency comb generation can be seen. And many of these platforms, in particular in last years, share the common feature that they chip integrated. And the materials that in which this process has been observed are in particular silicon nitride. There was the first integrated platform that was pioneered by Michal Lipson that also showed that it's possible to generate Kerr frequency combs not only in ultra-high Q resonators but also in devices that are chip integrated. And then in more recent times, there's been a very large proliferation of different materials, which includes diamond, aluminum nitride, L-gas, gallium phosphide, and also most recently lithium niobate. And so these recent two additions are particularly interesting and promising. And the reason is that they not only have a chi3, but also a chi2. So these are materials actually that don't have inversion symmetry. And that opens the door to combine actually the third order nonlinearity with the second order nonlinearity in kind of photonic integrated devices. Now, the combs that you can generate in these integrated devices, they share a few common features. One is that they have large bandwidth, limited by transparency and your ability to engineer dispersion. And also they have bandwidth that can achieve here almost an octave at high repetition rates. And the repetition rates are essentially featured or limited by the largest microresonators you can make. And so typically in these integrated devices, you have rep rates in the range, as I will describe, of conventionally 100 gigahertz. The lowest that can be done today is about 9 gigahertz, whereas these bulk approaches can even go to just 1 gigahertz rep rate. Now, one comment deserves notion. This this view of 4-wave mixing that I've described, whereby an initial pair of sideband cascades, that applies to some resonators, but only to those that have a ratio of the line width kappa over dispersion that's equal to 1 or smaller than 1. So for devices where the dispersion of the resonator is larger than the line width. Now, for many integrated devices, this is not the case. And the reason is that in integrated devices, you typically have a much larger cavity decay rate. So the cavity decay rate kappa typically is much larger than dispersion. And this implies that if you look at two adjacent free spectral ranges, you would not immediately see the walk-off of the free spectral range. And this has some profound consequences for the 4-wave mixing I've described. And the consequence is that as you pump the resonator, your first pair of sidebands are not generated on adjacent free spectral ranges, but rather actually they're moved out many FSRs away. And in fact, that ratio of root kappa over D2 is the first pair of sidebands. So it's a number of free spectral ranges you skip, due to the fact that your parametric MI gain lobes, peak, far away from the optical carrier. And this implies that you generate a comb, what we call a primary comb or native comb. And once that primary comb is generated and you have strong kind of sidebands, those can undergo also 4-wave mixing, in this case non-degenerate 4-wave mixing, and cause the formation of subcombs. So all these subcombs here have the same kind of free spectral range, the same kind of mode spacing, except that the carrier envelope frequency need not be the same. So these are all kind of subcombs that are coherent within themselves and also mutually coherent, but don't share the same grid. And that leads, if you pump stronger, to the formation of a very complex interplay of all subcombs and the generation of a very complex kind of mixing product. And one of the consequences that you have, which is not very intuitive from a nonlinear optics perspective, is that one single cavity resonance can have multiple optical laser lines that are actually feeding it. And this can be corroborated in experiments. This is an example of a MAC fluoride resonator. The Q is exceptionally high, but the dispersion is almost zero. So therefore, you again have this formation of these subcombs. And if you do a high-resolution spectroscopy, what you see is that underneath the cavity line, which is shown in gray here, you have many optical combs, many lines. And these are all the different mixing products of these subcombs merging. And now, and so that's again a feature for systems that have a line width that's large and a dispersion that's small, which is typically the case for integrated devices. Now, what is very interesting is that there's a process in nature, and that I'll spend quite some time talking about today, that promotes the formation from such kind of a spatial temporal chaos of states that have very high coherence. And that process, what leads actually to coherence, is related to the formation of solitons. And if you initially see the spectrum here, you would not guess and imagine that you can make this spectrum of kind of laser lines that are very erratically spaced, that you can make that fully coherent. But in fact, there is a process, and that's spatial temporal self-organization via dissipative Kerr solitons, dark or bright. So this process has been observed in previous works, and it's related to actually some earlier studies that were made by Leo Halterman in Brussels. This process of dissipative soliton formation also is promoted in optical microresonators. So here again is the crystal resonator I just described that generates this chaotic waveform. And this chaotic waveform can also be seen in the spectrum. So if you look at the spectrum, and here the laser is scanned, this is time. So here the laser is coupled into the cavity. Okay, at this point here you reach a bistability point, so where the Kerr frequency shift is approximately half the line width. You see the formation of combs, then subcombs, then this chaotic region where subcombs merge. Okay, that's why here the oscilloscope shows these oscillations. And this is concomitant with a beat node. Okay, so that's the beating of adjacent comb teeth that's very broad. And again, this is, in reality, these are many, many comb teeth, again, feeding a single cavity resonance, leading to a chaotic waveform. But now something interesting happens. When you tune, okay, past your tilted Kerr resonance, so what happens is, actually, you see suddenly a region occur where everything becomes suddenly very quiet. And in this region here, you see steps. And in this region, also the beat node suddenly collapses. So that's indicative of a coherent state inside the cavity that has been fed, okay, by this incoherent noise or incoherent state using the modulation stability or Kerr comb formation. So what is happening here? You can simulate this process. So this is our propagating numerically the coupled mode equation. You see that actually there's a region of instability. And once you cross this point here where my laser pointer is, which is the zero of the resonance or the peak of your tilted cavity, what you see is the formation of a soliton is appearing. And so this last step here, okay, this step here is where you have a single soliton inside the cavity, and this has a secant hyperbolic spectral envelope. Now, let me make a remark on kind of the mathematical basis of these solitons. So what was shown in this last simulation here is just numerically propagating, okay, the coupled mode equation of 4F mixing. Okay, so AMU is one mode of the cavity. Okay, you can choose a grid here. In this simulation, there were 100 modes used. Each of these modes decays with the cavity decay rate kappa. Okay, there's one continuous pump here that acts on mu naught, so our pump frequency. And then there are the various kind of terms due to 4F mixing. So this term here, this product of three operators of three fields, describes self-phase modulation, cross-phase modulation, and the 4F mixing gain. Now, the reason that you see solitons in this numerical simulation is that this equation, which is nothing else than a frequency domain representation of 4F mixing, you can also write in time domain. Okay, and in time domain, this equation might be much better, maybe known to many of you. If you do this in time domain, you can do it with a mean field approximation. So A now is the envelope actually of the field inside the cavity, whereas AMU here was actually just the strength of one of the comb components. And this mean field equation is a driven dissipative detuned, okay, nonlinear Schrödinger equation. So the left-hand side here is something many of you recognize. That's just a nonlinear Schrödinger equation. That's lossless, that's conservative, okay, no loss included. You just have dispersion, you have nonlinearity. And if you neglect for the moment the right-hand side, the solution of this equation actually are solitons. But there's a modification of this equation that deserves attention, and that is the following, that this equation, in fact, is dissipative. Okay, so it has here kappa over 2, so the intercavity field decays, because obviously cavity has a loss rate. There's also a detuning, and this detuning captures the detuning of the cavity with respect to the laser, and then there's a last term here that's a continuous wave drive. And so this is an equation that goes now under the name Lugaro-Lefebvre equation, and it's a damped-driven detuned nonlinear Schrödinger equation. And it can also be written here in this dimensionless form. And I want to spend kind of one moment to actually look a little bit at the history of this slide. So where is this, history of this equation. So where does this equation come from? So it turns out that this equation has been studied yet in another different field, and that's in the field of chemistry and biology. So in the very early work of Prigogine, Prigogine was looking at chemical reactions where you have also a system that's driven. And if you have chemical reactions that are driven, there is also a phenomenon of spatial temporal self-organization. So in reactions, what you can observe is also the system starts to self-organize, creating patterns, creating stripes, creating formations as shown here. And Lefebvre's contribution has been to understand that you can actually map this spatial and temporal self-organization of a driven dissipative system also to the optical domain. And that's actually what he did back in 87 in his Lefebvre equation, where he looked at spatial dissipative structure in passive optical systems and recognized that also in these systems you should form kind of patterns. And the patterns that are relevant here are the patterns in particular of dissipative solitons. So how does the solution look like of this Lefebvre equation? Well, the solution of that equation is a continuous wave background inside our microresonator with a soliton that is locked to it. Okay, so opposite to kind of a fiber soliton propagating down a fiber where there's no background, these solitons are locked to their drive because it's the drive that continuously replenishes and compensates the loss. And so these solitons are also known under the name dissipative solitons, and they rely on this double balance of dispersion and nonlinearity and gain and loss, in this case parametric gain and loss. And so dissipative solitons are used actually in a variety of systems. As described, in fact, they exist in plasma physics, which have been observed early on. They can be injected and generated in optical fiber cavities by propagating a very strong pump laser, okay, so-called holding field in a fiber loop, and injecting a small pulse that is consecutively trapped actually by the holding beam, or in mode-locked lasers. And there's also another variant of this soliton that doesn't occur in a time domain, but rather in a spatial domain. And these are called spatial solitons. And again, they're described by the same equation, except now they don't describe a self-organization along the azimuthal coordinate of the resonator, but rather across the transverse extent. And these are called spatial solitons. But again, it's important to realize that the underlying description of all these phenomena, be it in plasma physics, optical fiber, mode-locked lasers, or spatial solitons, that can all be traced back to this driven, detuned, damped nonlinear Schrödinger equation. So if you look at the LLE, at this equation, now written again in a not normalized form, where D2 is our dispersion, G is our Kerr frequency shift. Okay, so colloquially speaking, what G is, it tells us actually how much the one intracavity photon shifts the optical cavity. And then we have again here our detuning and our loss and our continuous wave drive. And if you take that equation and solve it, you can plot a so-called bistability chart or kind of phase diagram. And the horizontal axis here is the detuning of the laser with respect to the cavity that's driven, and the vertical axis here is the power. Okay, and if you look at low power, of course, there's just the continuous solution, so there's no kind of parametric oscillations. If you increase the power, there's the onset of the bistability, where you form a region where you generate Kerr combs, and this is also known as modulation instability. So again, the sidebands are a consequence of MI and form, and within this region you have regions where the comb formation can be either completely coherent, okay, or where it can be incoherent due to subcombs merging. So this is actually a simplified diagram where in reality there's more states than are seen here in this blue region. Now if you cross that region, you first come to a region called breather solitons, where you form solitons but whose temporal envelope actually changes with time. Okay, these are called breather solitons. And crossing that further, you come into the stable soliton region. And so again, these are just the solutions, okay? And but from this chart, you can learn quite a bit. In particular, what you can also understand is how to generate non-solitons. Because the way you need to generate solitons is you cannot just simply take the laser and move the power up from a given detuning, because this diagram in itself drives or describes a driven dissipative system. So in order to reach a soliton state, what you have to do is you have to first generate with modulation and stability kind of sidebands or spatial temporal kind of pattern, then cross the breather region, then you enter actually this soliton region. And this chart here, going from MI to stable soliton, is what I'm going to show on the next slide for an example. So what you see here is a optical resonator. You see the laser scan. So first you generate kind of primary sidebands or primary combs. So you are in the blue region, this modulation and stability region. Once these start to merge, you generate spatial temporal chaos. You're still in that blue region, okay? And once you start crossing the cavity, okay, there's a very brief region here that's hard to discern. That's called the breather soliton, where in fact there's an oscillation that you can barely kind of make out at the interface of these two states. And then there is a generation of solitons. And here in this case, there's a number of solitons you generate. These steps here are quantized. They just describe you immediately how many solitons you have in the cavity. And this last step here is a single soliton. So these are, in this case, 4 solitons, and then all the way to a single soliton here at the end. So these solitons have a number of properties. First of all, one of their features is that they can have very high repetition rate. okay, because the round trip time across the resonator can be very short. Okay, and so in this example here, for a crystal resonator, the rep rate is about 14 gigahertz. In addition, the pulses can be quite short, so you can generate pulses that are in 100 femtosecond and even tens of femtosecond range, and you have a numerically predictable spectral envelope. Now, if you look at the spectrum, there's a couple of things that deserve notion, also they're not so intuitive. Okay, the first thing you see is that the pump laser is much stronger than the soliton. Okay, and this is a so-called bright temporal soliton. And the reason that is because it has to do with the original kind of bistability that we're exploiting to generate the bright soliton. In fact, it's a feature, okay, that's linked inherently to the bright soliton formation. Another interesting prediction I want to draw attention to is that the soliton duration in such a system is tunable. And so the further the laser is detuned from the cavity resonance, the shorter the pulse will become. And that's actually quite a not intuitive kind of relation. And let me show this. So here what's shown is, again, our picture of the Kerr tilted resonance. So if the resonance is tilted into the bistability regime, you can think of the soliton as sitting here as a combination of the laser being far detuned from the original Kerr tilted resonance. This is the C resonance. And the upper branch, which is called the S resonance. So you're exploiting this bistable region to form actually the soliton, being composed of the continuous wave background and the soliton. And this immediately explains now to you why actually there's this large separation of the pump to the first sidebands. The reason is this laser C here actually is very far detuned from the cavity. And let me give you one example that shows you how strikingly far detuned you can be. This is an example where the S and C resonance, okay, are separated here by a few kappa. But now if you detune the laser further, you see a massive increase in bandwidth. So I'll do it one more time. So this is the original kind of laser that's detuned by 5 megahertz from the cavity. Now you detune the laser, okay, almost 25 megahertz from the cavity center. So that's in this case about 20 or 30 line width away. Okay, and the soliton actually becomes shorter and broader. Okay, and again, it means, and this far detuning here from the cavity of 25 megahertz, okay, that explains why there's this large contrast here, okay, for the bright soliton. So bright soliton formation, where the pump laser is in the lower branch, actually inherently, okay, has low efficiency. In contrast, if you use dark soliton, actually you reverse the CNS resonance, and you can remove that penalty from the laser detuning. Nevertheless, you generate exceptionally short pulses in certain cases that I'll describe. You can have typical conversion efficiencies, say for 100 gigahertz soliton, that are typically in the % range. So another interesting property of, and surprising property of solitons is their robustness. So you may think that, and intuitively expect that solitons only form in a highly idealized system. But what has been observed in recent years is that the soliton formation, okay, always finds ways to find a state that is shape preserving. And here I give you an example of first a almost perfect variation of the free speckle range. So this is a plot where what we plot here is not is the resonance equidistance from, or the deviation from an equidistant grid. If you have a parabolic variation, that's anomalous dispersion. Okay, and this mode family here sees very, very little deviations. In contrast, the lower one here sees so-called avoided mode crossings, and these come from the fact that there are many, many modes inside an optical resonator, and they can mix, cross, and couple due to various imperfections, purposefully or accidentally. And if you look and zoom in on this modes crossing here, what such a mode crossing will do to the soliton is it will promote the generation here of a dispersive feature in the soliton spectrum. So despite having a mode crossing, the soliton will still exist, it will still find a solution that is self-similar, and it will still sustain. And that's part of the reason why even in imperfect systems, you can still promote the formation of these dissipative Kerr solitons. And you can see these kind of spikes here, these are all single mode dispersive waves generated due to avoided mode crossings. Now, you can also explore that effect to your advantage. And this is an example here where what was done is, this is work from Kerry's group at Caltech, where they exploited not an accidental mode crossing, but rather a purposeful mode crossing by exploiting effectively the crossing, okay, of the effective index of two different mode families. And when mode families cross and couple, okay, they will form a symmetric and asymmetric mode pair. And one will have a normal GVD, and one will have anomalous GVD. And that anomalous GVD allows, therefore, to even promote the formation of dissipative Kerr solitons in windows where the material dispersion is normal. So in their case, they went from 1550, where you have anomalous GVD in silica, to 1 micron and even to 750, and there's even a possibility to go to the green by exploring, okay, this mode hybridization to engineer dispersion. looking again at Kerr frequency combs platforms to date, and now looking again at the question in which platforms Dissipative Kerr Solitons have been observed, they're comparatively less platforms. And so the platforms where these DKS have been observed are primarily mag fluoride, silica, and also silicon nitride, and most recently also lithium niobate. And that's again very exciting because here you're combining actually the second order linearity with the third, and that might actually give way to some possibility to do tuning. And there's actually also talks here at this conference I'm highlighting. So there's been, over the last years, significant advances in understanding dissipative Kerr solitons, and I'll not mention all of them, but let me give still a list. So it's known that solitons can switch, so you can, it's also known that they exhibit a Raman cell frequency shift as solitons in conventional fibers. Breathers have been observed, so dissipative Kerr soliton breathers. And what's particularly important, and I won't emphasize, is that dissipative Kerr solitons, as described here today in the tutorial, they're actually only one form of spatial temporal self-organization. There's another one, which are dark pulses, okay? And those have been observed by Andrew Weiner. They're also called platicons. And they are also coherent states of recirculating pulses, and they also exist in a normal dispersion regime. Now, again, there's another list of advances I won't cover, but I want to mention simply that also there's interesting effects that can be related to so-called cavity supersolitons, Stokes solitons, and so the whole rich nonlinear physics that you can explore in these kind of systems. Now, one aspect I want to spend a little bit of time on is to look at the ability to generate these dissipative Kerr solitons in photonic integrated microresonators. And this is interesting because it really links to the community of integrated photonics to those of frequency metrology and solitons. And a very important step in this context has been the observation of Kerr comb generation in silicon nitride, which was first done by Michael Lipson's group, by Levy et al. In 2012, where they observed that it could also generate in silicon nitride Kerr frequency combs, and thereby look at the possibility also generate solitons. Now, silicon nitride is a particularly interesting material because opposite to silicon, it has a wide band gap, 5 electron volts, so it has no 2-photon absorption in a telecom band. It has also transparency from mid-IR to the visible, and it's also a space-compatible material. So one of the key drivers for observing solitons in integrated photonics is the ability to dispersion engineer. Okay? And if you have a silicon nitride waveguide of a certain height and certain width, one of the advantages is that you can use the geometry to tailor dispersion in ways that you not only control the second order dispersion, but also the third and fourth order. And here's one example where there's a silicon nitride waveguide where the height is varied. And what you see here, again, is this D-end profile. So parabola open to the top here is NML's GVD. And what you see here is that there are intercepts with zero crossing. And those intercepts here are regions where the dispersion switches sign and then compensates all the NML's GVD you have accumulated. Okay, and as we'll see, is actually that point actually allows the formation of dispersive waves. Now, any resonator made from an optical waveguide will allow to engineer dispersion. And the reason is that if you look at the effective index of a mode confined to, for instance, this waveguide, what you'll see is if you're at short wavelength, well confined in silicon nitride, your effective index effectively follows that of the core. Whereas if the wavelength is longer, you effectively delocalize the optical mode and you will go to the cladding. Okay, so you always have this sigmoid kind of behavior. And this sigmoid has a curvature that varies. Okay, the curvature here is negative, the curvature here is positive. And that's exactly the reason why in waveguides where you well confine the light inside the core, you have NML's GVD. So whenever you have tight confinement, you generate NML's GVD. Okay, this is this parabolic region here. Whereas if you are delocalized, you have normal GVD, which would be the region here kind of on the long wavelength side. So those points where the dispersion intercepts give rise to a very interesting phenomena that's known in the supercontinuum community as Soliton Cherenkov radiation. And that is the following, that if you have a soliton that extends into a normal dispersion regime, and at these points where d is equal to 0, you create, in fact, the formation of a dispersive wave. And this dispersive wave is an oscillatory tail that's bound and co-traveling with the soliton. And this dispersive wave process is precisely actually what gives supercontinuum generation in photonic crystal fiber this visible spectrum. That visible spectrum is a normal dispersion regime, and it's a dispersive wave actually that's coupled to the soliton. Now, in the case of integrated photonics, what's interesting, and has been predicted by Stefan Cohn early on, is that you can generate very broadband combs. And here, again, the reason this is possible lies in the dispersion engineering, in the dispersion properties of the waveguide. And so this is a numerically predicted spectrum, which again has this, this feature of this enhanced power in the wings. Now you can also observe this in experiment. So if you pump a silicon nitride resonator, you see here the pump at 1550, and at 1.9 microns, about 155 terahertz, you have the d equal int 0 point, and you can see here that there's a formation of a dispersive wave that gives you power in the wing of the comb. Now this is the experimental spectrum, and it's interesting to compare that to numerical modeling. And as you can see, the model shown here in gray shows exceptionally good kind of agreement. In fact, there's a slight deviation, and that deviation comes from the fact that the actual soliton and the experience is a Raman cell frequency shift that was not based in the simulation. And you get perfect agreement if you include these terms. And today, these Kerr frequency combs, they are numerically simulated with a variant of the LLE equation, where you include also thermal effects, you can include higher order dispersion, you can also include the Raman cell frequency shift and the shock term, and you can obtain a very, very high degree of precision by which you can predict the location of dispersive waves and also the shape of the spectrum. Now, in this context, I want to emphasize that these numerical simulations have become quite widespread, and there's even now tools that can be downloaded from GitHub. This is an example here from NIST, where they have programmed in Python a very fast LLE solver that allows to simulate hundreds and hundreds of nodes in a very fast fashion by using Julia, a language optimized for numerical computation. And this shows here an example of a typical scan across a resonance. So you see the MI, you see the Soliton step, and here's the intercavity waveform and the optical spectrum that shows here the formation of two dispersive waves. And as mentioned, in fact, if you have two zero crossings in the integrated dispersion, you will form dispersive waves with two kind of enhanced spectral power in both wings. So this is the example shown here. So there's a D-in profile. You have a crossing on the long wavelength side and the short wavelength side. And if you look at the spectrum, you see two dispersive waves here appearing symmetrically. Another example that I want to draw your attention to is the case when you have Raman. So in the case of Raman, you might have anomalous GBD, but you can actually promote the formation of a Raman soliton. These are also called vector solitons. So here, in fact, there's a second soliton generated that is seeded by the first soliton and coherently bound. So it's a bound entity. And in the middle is a very important case that I'm not going to discuss in more detail, but I want to draw your attention to. These are normal dispersion combs. So here the parabola is inverted, and via mode crossing you can excite so-called dark pulses. Now, the integrated photonics, as described, allows to generate these dissipative Kerr solitons also in very compact kind of devices. And of course, you can then exploit those for different applications. And I'd like to review kind of a few applications of dissipative Kerr solitons. Now, the first application that comes into mind is to use the fact that you can easily operate two solitons on two separate chips to look at dual comb spectroscopy. And that was done early on in the group of Kari Bahala. So here actually are two DKS generated in two silica devices. They're not on the same chip. This is an image I've taken from our work here, but it doesn't describe the experiment here. So these are two different kind of solitons pumped by two different lasers, and you can see here the optical interferogram from the bead node, and you can pass those through, say, two molecules through a gas phase and observe the dual comb interferogram. And this dual comb technique, again, is quite well known from conventional fiber laser frequency combs, but can here be generated using the DKS as comb states. Now, of course, to generate very highly coherent dual comb spectra, the mutual coherence is of central importance. And here what you can do is you can exploit the fact that you can generate dissipative Kerr solitons by pumping both clockwise and counterclockwise. And this was shown by Alex Gaeta and also by Kari Bahala in two separate works. And the idea here is to exploit the fact that whispering gallery modes are intrinsically degenerate. Okay, so they are whispering degeneracy with respect to the angular mode number. So you always have a clockwise and a counterclockwise mode that, if you have very little splitting, okay, are frequency degenerate. So if you pump from two sides, okay, you can generate two soliton pulse streams, and you can either use the Raman cell frequency shift, okay, or the laser detuning, okay, to break the degeneracy of the two repetition rates and generate dual comb interferograms. And those are tremendously useful. So you can use those, for instance, in LiDAR for ranging. You can also use them for spectrometer calibration and other applications of DKS, where you exploit the fact that you would like to have mapping of the optical information into the radio frequency domain. So this is an example, again, of this counterclockwise-clockwise scheme. So here, again, you generate, with one single laser now, okay, two Soliton pulse streams. You break the degeneracy in this case by offsetting the laser frequency slightly. And you see here the dual comb interferogram. And if you look carefully, what you see is that one of the comb teeth, in fact, okay, extends, or one of the beat nodes extends to DC. So what you have done here, in fact, is generated a dual comb interferogram, okay, that's folded. Okay, and you can easily unfold numerically by doing IQ detection. But nevertheless, you have one of the comb teeth that hits here the DC. Now you can also go to higher offset frequencies, and you can use a variant of this scheme. Again, using either clockwise, counterclockwise configuration or co-propagating configuration. And that is to use different spatial modes of the same resonator. So every microresonator has a whole series of transverse modes. That comes from the fact that you operate in the NML CVD region where you have tight confinement, so you are typically where you're multi-mode. And so what you can do is you can pump with two different lasers that are phase locked, okay, two different dissipative Kerr solitons and generate two pulse streams. And these two pulse streams won't share the same repetition rate because higher order modes are more tightly bound in the interior of the resonator and experience a different round trip time. Okay, so you can intrinsically have a dual comb interferogram. And this is an example of such an experiment. You take two pump lasers here, you excite two DKS. You have shown in red here the first pulse stream, and blue the second pulse stream. Those are in this case co-propagating, and the difference in the interferogram here is about 4 gigahertz, and you have about 600 kilohertz of rep rate difference. And so now if you plot the interferogram, again you have here the sequence parabolicus mapped into the RF. Okay, these are about a few hundred comb teeth that you have. And you can now derive both the amplitude and phase information and use that for a kind of proof of concept kind of spectroscopy experiment. And so how would it look like? You can, again, use these clockwise, counterclockwise combs. You can run through a wave shaper. You program in a wave shaper like an amplitude in red and a phase profile. And now you can use the interferogram. You use the real and imaginary part to reconstruct phase and amplitude, and that's shown in a dotted line. So this kind of works, and as expected, and shows you can extend DKS kind of also to dual comb spectroscopy. You can also do triple combs, and here there's an actually interesting piece of physics you can learn, and that is the following. If you have combs that are counter-propagating, you will not have, in an ideal system, intermodulation products. Okay? In contrast, if you have combs that are propagating in the same direction, okay, the solitons will meet each other. There will be cross-phase modulation, and if you look carefully, you see in this moire pattern, in fact, comb teeth. Okay? So what happens, each comb teeth here is modulated, okay, by setting the intermodulation frequency here to something that's very close to the cavity decay rate. And you can avoid that by going to counterclockwise configurations. Nevertheless, it shows kind of that you can even generate 3 or even more kind of solitons in the same optical resonator. Now, let me also comment that these intermodulations, you can also make them vanish, and all you have to do is make the difference in repetition rates larger than the cavity decay rate, and that way, actually, the intermodulation products are filtered. Now, over the last years, I said there has been many advances in addition to these counterclockwise solitons that I won't review, and I want to spend a little bit of time on applications that have been shown so far of microcombs. And so the ability to generate these combs in chip-scale devices has, in the last years, allowed a number of kind of system-level demonstrations. And this is an example here from KIT and also collaborating with us, where the DKS were used in a system-level demonstration for coherent communications, and where IQ data with up to 50 terabyte per second on 98 channels was transmitted. And here, what was in particular exploited is the fact that each of the generated comb teeth inherits the same phase noise as a pump laser. And the challenge of the low power per comb teeth in such system can typically be compensated or accounted for by very strongly overcoupling the resonator and using typically strong pump lasers to pump the device. You can also do very fast ranging. So this is a proof of concept of exploiting the very large repetition rate and also the large bandwidth. So in this case, actually, a projectile was flown with 0.4 Mach. So it was a projectile air gun pellet. There was reflection measured from one comb. There was a second comb used as a local oscillator. The dual comb interferogram here had extremely high frequency, 18 gigahertz. And this allowed to measure here 12 nanometer RMS in 40 microsecond, and then obtain the spectral envelope of the projectile in kind of real time while it flies. Another particularly fascinating application was shown by CSCM, by Tobias here. And he used a Silicon Nitride resonator with a very low repetition rate, in this case 28 gigahertz. In order to promote solitons, he did not employ a continuous wave pump, but he employed, in fact, a pulse pump. And the pulse pump, okay, has the distinct advantage that it gives a higher conversion efficiency of the pump power, okay, to the soliton. And with this technique, he showed that you can do astrophysical spectrometer calibration. And why would you like to use a dissipative Kerr soliton for this purpose? The reason is that for astrophysical spectrometers, to be able to distinguish adjacent comb lines, you need to have a repetition rate of at least 10 to 30 gigahertz. Okay, so very large repetition rate in the conventional kind of sense. And so this is kind of an ideally, or matches very well with low rep rates in silicon nitride. And there'll also be a talk here at this conference. But I still like to highlight the particular use of the pulse scheme that was used in that experiment. So that experiment differed from the ones I've shown earlier in the use of a modulator comb. Okay, so not a CW pump, but rather a pulsed pump that's shown in red here that gives better temporal overlap with the dissipative Kerr soliton. And that can be immediately seen in the conversion efficiency. So here in the middle, you see actually at 1550, okay, the pulse driving, and you see here the formation of more than 2,000 lines, okay, spaced here with 28 gigahertz of the dissipative Kerr soliton that is locked, okay, that frequency or that follows in time, okay, the optical pump, okay. Another example that shows kind of the connection to, again, frequency metrology and chip scale kind of frequency synthesizers is shown here. So these two slides here, this chart is from NIST. What you see here are two recent kind of DARPA programs, ACES, which aims at making an atomic clock with enhanced precision and stability. And the second one is DOTAS to make a digital on-chip synthesizer. And both utilize, okay, in this case, integrated photonics, both for the laser, for the doubler, okay, for splitters, as well as for optical amplifiers, typically done in silicon photonics, and leverages the high Q resonators both in silicon nitride and silica to generate interlocked clockworks. So here you see a dual dispersive wave that's harmonically related by a factor of 2, so you can use that to measure the K envelope frequency. And there's a second comb at 15 gigahertz that use the heterodyne that beats the spacing here of the terahertz comb. And so what? So the vision that's shown here is still, still not realized in lab. But what you have to realize and acknowledge is that many of the components, okay, already exist today. That is certainly the case for the lasers, for the amplifiers, for the resonators, and technology is there to create these very, very compact kind of chip-scale atomic clocks as frequency synthesizers. Now, let me mention that for many applications, be it terabit coherent communication, be it for dual comb spectroscopy, or distance measurements or atomic clocks, one primary, of course, concern to make an integrated device is power. Okay, and so a common challenge in the field has been the efficiency of soliton generation or Kerr comb generation, and the pulse pumping is one way to increase that. And I want to spend just a few minutes on giving some advances that have been made in the field to generate very low loss integrated photonics. And it suffices by starting to say that integrated photonics still has losses that are many orders of magnitude away from optical fiber. So if you have an optical fiber today, losses are 0.5 dB per kilometer, whereas in integrated photonics, okay, the losses typically are, in the best case, dB per meter. So there's still kind of a 3 order of magnitude discrepancy between what you can do in optical fibers and in integrated photonics. And the question is that a fundamental trade-off or not? And I'd like to describe some advances that were made to actually try to approach, okay, the limits, or at least eliminate some of the common origins of loss. And one common origin of loss, okay, especially in subtractively processed devices, comes from scattering. And so this is a process that was developed to make integrated photonics by not etching silicon nitride, but rather to create preforms that you fill with LPCVD and then polish. And that's a process that is well known for those in semiconductor industry. The same process where the dielectric is replaced by copper is called the copper damascene process. And if you apply that process to integrated photonics, you can make waveguides that have high aspect ratio and also alleviate some of the common problems with silicon nitride, such as crack formation. And this process generates waveguides that are completely conformally coded with SI2 and have line width here on the order of tens of megahertz, and also give rise to very kind of low kind of defects due to the absence of void formation, which is typical in kind of cladding of integrated photonics. Now that process still does not solve all the challenges. There's still roughness, okay, in the system, and that's a common kind of culprit for integrated photonics. And what you can do is, by applying a reflow, okay, to the SI2, you can generate integrated waveguides that have exceptionally low roughness. So this is an example where you take a finished wafer, okay, you put it in the furnace at 1200 degrees, you reflow, you still retain all the conformal properties, okay, that's a completely deterministic process. But now actually the line width of the devices, as shown in this histogram here, collapses to values of less than 10 megahertz. So that means that the most probable line width you will find in this chip, as shown in this histogram, is something larger than 20 million. Now that's still far away, actually, from the limit. And in fact, what we have learned in the last years is that part of the limitation that we're starting to see is very similar to that of fiber optics. We're starting to see actually metal impurities to start dominating internal absorption. But these devices actually rival kind of roughnesses that you can obtain also in tapered fibers that you draw. So losses are expected to be in the hundreds of millions. Those devices give solitons almost every resonance, so very reliable, and also allow to make very compact chip-scale driven combs. So now linking back to the first part of the tutorial where I mentioned the DARPA vision of making a completely chip-scale synthesizer, how close are we to this? And I'd like to show two works that show kind of the most compact comb devices to date. One is shown here where you have an indium phosphide chip coupled to a silicon nitride resonator. You exploit this photonic damascene process not just to generate Kerr combs, but also to promote injection locking. So that's a DFB diode that has a line width of 10 gigahertz. It's first injection locked via backscattering. That narrows the line width to about 100 kilohertz. And if you operate in the right regime, you can also promote the formation of dissipative Kerr solitons. And this entire device here computes about 1 watt of electrical power. And there's a similar, and this is here a pump laser, in this case of indium phosphide, that just butt couples. And you can also generate this with even simpler way by not using a laser, but rather just an SOA that has high reflectivity at the end. So showing here a chart from Michal Lipson's work, where she has a SOA that has a front facet just cleaved, coupled to a silicon nitride photonic chip with additional vernier filters for tuning. And also here you can generate a dissipative Kerr soliton, okay, with power levels, okay, that are in the 100 milliwatt electrical power. So it shows like that you're very close to believe, in this case, even a battery operated device. You can also go to low rep rates. So this is work where dissipative Kerr solitons now are generated at 10 gigahertz. So you can use that to make microwave synthesizers. And if you look at the phase noise, without going to too much detail, I'd like to mention that you can actually get quite competitive phase noise compared to commercial electronic synthesizers. Okay, certainly not to frequency division with optical reference cavities, but still these are very competitive phase noise in devices that operate both in the X and K-band regime, so 10 gigahertz and 20 gigahertz respectively. And that also shows that with these macroscopic kind of resonators and these very low losses, you can really bridge the gap kind of to low rep rates as you would typically use from fiber optics. Now with this, I'd like to mention that there's many applications of dissipative Kerr solitons. Okay, the applications encompass, as described, astrophysical spectrometer calibration, coherent communications, ultra-fast distance measurements, atomic clocks, frequency synthesizers. There's a large emerging area of integrated microwave photonics where you can use them for. And there's territory to investigate, in particular in the context of biomedical imaging, be it OCT, be it Raman, or be it other techniques, and also for low noise microwave generation. And with this, I'd like to thank you for your attention and look forward to questions.